Good morning. Today we're gonna talk about a special case with continuously distributed load in a one-dimensional member. So up to last time that we discussed one-dimensional problem with multiple concentrated load, and then I explain you the different analysis procedure, starting from the force equilibrium, and then we check the material load, and then we finish our analysis checking the displacement compatibility. And then the other choice is we start from displacement compatibility, and then we do check the material law, and then we finish our analysis by checking the force equilibrium, isn't it? So, before any step of our analysis, we shouldn't forget the definition or choice of the coordinate system. So otherwise, make sure that the loads, the external loads and the reactions, they are given in the form of vectors. So if you don't prescribe the definition of coordinate system, it is difficult to handle the vector components. So make sure that the vector itself, vectors themselves do not have any signs, do not have any signs. They have only the magnitude and the direction. But if you consider vector components, the vector components always has a sign, it's a sign, depending on whether it's in the direction of positive direction of the coordinate or in the negative direction of the coordinate, Alright, so today let's talk about a problem, the bars with continuously distributed loads, as given in the figure. So here, for simplicity, we want to consider the left hand side is fixed, and then we have free end here, and then we do have a continuously distributed load, and then its magnitude depends on the coordinate. So make sure that although the coordinate is omitted here, but this is our coordinate, this is our coordinate. And then starting from this origin, so we'd like to indicate that point with x, the position of this point is x. And then we want to consider the total length of the member is given by L, capital L. And then also one of the interesting point is that the cross-section area. So make sure the last time we considered always constant cross-section areas, isn't it right? Constant cross-section areas. But now also in this example, between the nodal points, so we didn't consider any change of cross-section area. Also here, between node B and node C, the cross-section area is fixed as a constant. But here, the cross-section area is also changing. So which means we have to write the cross-section area as a function of the coordinate. It depends on the position, It depends on the position. Alright, so now we want to check a small segment, the position of this small segment is completely arbitrary. So you can choose this segment from here and also here. So we want to consider an arbitrary point measured as x here, then which means this is also x, The left point of this segment is measured as x. And then if you look at the right hand side, this is what? Because the thickness of the segment is dx, then the coordinate of the right point is x plus dx, isn't it? X plus dx. Is it clear? So if you look at the forces acting on this small segment, then first we may consider the external forces. The distributed load is given by a function px, and then we must have internal forces, okay, internal forces. And then because the loads are continuously changing, if I plot the possible change of load would be look like this. So in x coordinate, if we monitor the change of the internal force nx, then it may work like this. It may change like this, isn't it, right? The function of x coordinate. Okay, so let's say I want to consider a point here, what I mean the left point of this lecture note, the left point here, and then let's consider the change of segment dx. So we are here. Then let's say we have nx here. Okay, so I'd like to approximate this value. So with respect to this nx, the internal force measured at the position of x, then how can I do that? So n at what I want to know is the internal force at the position of x plus dx. That's what I know, isn't it? X plus dx. That's what I want. But this can be approximated as what? Approximate as nx plus. And then we want to check the change of internal force with respect to x coordinate, and then we'd like to multiply the change of x coordinate. Okay, and then you can find this relation by using the Taylor expansion tool. So simply we expand this internal force with respect to the current value of x, then you can obtain this equation. This is the Taylor expansion up to the first order differentiation. Is it clear? So now to make for detailed discussion, instead of using the internal force nx, so we want to consider the stress itself. So make sure that, so in any case, even for the derivation of the governing equation, so we always use the three conditions. So equilibrium, so material law, and compatibility. No exceptions, okay? No exceptions. So now we want to focus on this small segment, all right? Because this is one-dimensional problem. If you look at the left-hand, the segment, the cross-section on the left-hand side, maybe we must have the normal stress, sigma x. As I told you, the normal stress must depend on the position, okay? Must depend on the position. And then let's consider also the change of cross-sectional area. That depends on what? The x-coordinate too. And then for a general discussion, so we want to consider there is a change of elastic modulus with respect to the x-coordinate. This is a very general case. And then here, so we have a distributed load, the function of the coordinate x, okay? Okay, so now let's look at the right-hand side. If you look at the right-hand side, again, we must have normal stress, similar to the internal force, the normal stress also because this is function of x coordinate, it's changing like this. Okay, so at the point x, so we'd like to approximate the normal stress value, and this is x, and then this is x plus dx. We'd like to approximate this normal stress value. So by the discussion that we made just before for the internal force here, okay, similar to this, and then the normal stress at this position, the x plus dx, can be approximated by sigma x plus d sigma. So make sure in this equation, because we have dx and also dx, it is cancelled. That's why it is given by nx plus the change of internal force. So this point is very clear, isn't it? And then here, the change of the elastic modulus is also the elastic modulus measured at the left hand side, and plus the change of elastic modulus. Okay, and then cross-section area too. So I hope everything is clear to you. So now let's check the force equilibrium for this small segment. So this is a kind of free body diagram, because the whole system is in equilibrium and a stationary condition, which means a part of this structural system also is in equilibrium. Okay, so equilibrium says that for stationary system, sum of all the force components acting on this body, the free body, should be equal to 0. So I explained you before when I discussed Newton's second law. The equilibrium equation is the sum of force is still equal to 0 for a moving body with constant velocity. But we are talking about stationary system. That's why we don't consider any non-zero velocity. Okay, so sum of force should be equal to 0. So let's count the forces here. All right, the first we have what? By the way, sorry about it, I have errata. So I need to put minus sign here. I'll fix my lecture note. So here, if I choose this coordinate system, so local coordinate system, so the internal force acting on the left-hand side is equal to minus sigma x times the cross-section area. Because this is normal stress. So normal stress is what? The force per unit area. This is the definition of normal stress. That's why the internal force for the calculation of sum of all the force components here is equal to normal stress times cross-section area. And then right-hand side here, the right-hand side also, to calculate internal force, we need to multiply the normal stress. We need to consider multiplication between the normal stress and the cross-section area, and the normal stress at that point, and then cross-section area at that point. But we just approximated normal stress by this equation, and also the cross-section area here, isn't it? And then the distributed load is heading to the right-hand direction. We just consider the external force using this simple formula. Here the distributed load is what? The force per unit length for the structural system. Actually, to represent this precisely, so we have to write in this way to represent the distributed load. For example, we also need to consider the px plus sorry about it. So we need to consider this. So px and then dx, okay? Px and dx. It's a function of x coordinate, and we need to integrate from the x to x plus dx. And this is approximated as px times dx. That's why we have this equation. So otherwise, if the change of distributed load P is, if it is seriously changing, then we need to consider this integral form. By the way, because now here this is the integration operator, maybe we have to write this operator differently. Let's put the bar. Here the x is different from the x bar. So we use x bar only for the integration purpose. It's not the same of the original coordinate system. Okay, so if you from this second equation, then what? That becomes minus sigma a, and then let's consider the first term. Then we have sigma a here, and then let's consider the second term, and then second term. Then I have d sigma and dA. And then let's consider the second term and then the first term. That becomes sigma and dA. And then let's consider sigma and dA, yes. And the d sigma and A here. A times d sigma. And then the last one, d sigma and dA. So which means here, d sigma, this is a differential change, which means very small change, okay? Very small change. Infinitesimally very small change. And then the dA is also, because we are talking about smoothly changing cross-section. dA is also change of cross-section area over dx is also very small. So which means very small times very small becomes negligible. That's why we do not consider this. And then we have px dx, okay? So make sure that because of the sign, this is cancels. These two terms are cancels. So we have only these terms, okay? I told you that they are cancelled, okay? They are cancelled. So we have only this. Then because of partial, if you use partial integration, this becomes what? Sigma dA plus a d sigma means equal to d sigma and a, isn't it? So by the definition, sigma a is internal force. Okay? So this is what I told you. This is the simplified the result of previous calculation, and then using the partial integration, so we can combine these two terms to this, and this becomes the change of internal force. And if you move the right hand side, the last term to the right hand side, then I have minus p dx. So let's move dx to the left hand side, to the denominator. Then we have this equation. So the physical meaning of this equation is what? Change of internal force with respect to x coordinate is equal to the minus of the distributed load. Okay, this is pretty obvious, isn't it? So if you look at here, so we have, but if you look at here, maybe because of the external forces acting over the whole body of the member, then our internal force is maximum at this point. And then at very last point, because there is no the external force, then the internal force should be equal to 0. Basically, the internal force is decreasing, isn't it, right? So negative slope. That's why here we have negative slope. So now we can understand our derivation is correct, and then we can explain the overall characteristics of this governing equation intuitively. Okay? So although I showed you the mathematical derivation of the governing equation of one-dimensional bar subjected to continuously varying distributive load here, but it is very important to understand what you derived, okay, what you derived intuitively. So you need to, you have to be able to explain so what you derived intuitively, 직관적으로, okay. That's very important. Okay, and then further, the internal force is what? Normal stress times the cross-section area. The area is, the stress becomes because of material law. So up to here we use the force equilibrium. So now we want to use the constitutive law, the material law. The elastic modulus times the strain. And then let's move the area to just the position just after the elastic modulus. Then we have elastic modulus times the cross-section area. And then find the definition. So now we want to use the compatibility. The strain is equal to the first derivative of the displacement to the x-coordinate, du over dx. Okay? So now let's focus on the first term and the very last term here. So then it becomes what? It becomes N internal force is equal to elastic modulus cross-section area and then du over dx. Okay? So now let's move this guy to the left hand side. Then what happened? So du is equal to the internal force divided by these quantities and then dx. That's why, the displacement field, the function of displacement can be obtained by integrating du over the member. Then this is given by this integration. This is the full governing equation. So using this relation, so we can obtain the information of the internal force, and then the normal stress, and then strain, and then displacement field. Is it clear? Do you have any questions for the derivation of the governing equation? So these equations are called governing equations. Alright, so next subject is statically indeterminate structures. Okay, so because this story is rather long discussion, that's why I'd like make break here, the 10 minutes break, and we'll be back at 11.